Good afternoon, everyone, and welcome to our next IGLUNA student project show. IGLUNA is an international student platform coordinated by Space Innovation and bringing together student teams from all over the world to develop the technologies for the future space exploration. Our guest today is a student team P08 LIGHT2 from Greece, and they are developing the navigation helmet to help the astronaut discover the moon. I'm today live from Ferkar's House, the Swiss Museum of Transport in Lucerne, Switzerland. Unfortunately, due to the situation, our students were not able to travel to Switzerland, but they are joining us today online. We will start with the project show itself, and afterwards we will have time for the live Q&A session. So please use your chance to submit your questions on our YouTube chat, and we will discuss them afterwards with our students. Welcome again, and let's start with the video.
Welcome to LIGHT, a project aimed at finding creative solutions to problems arising in the space-related field using augmented reality technologies. This year we have recruited 10 new members in order to build upon the first team's work. In the near future, establishing an active human presence and exploring the moon will require extravehicular activities of greater scale and scope, performed in less time and energy expenditure than before. When it comes to navigating the surface using pen and paper maps, with craters as landmarks, is a difficult and confusing process for orienting and traversing areas fast. Similarly, the documentation and description of nearby areas needed for scientific fieldwork proves to be slow and cumbersome through traditional means. Lastly, the repair of faulty equipment is a complex, cognitively demanding task that requires extensive training. Having an integrated approach to tackling these issues and automating parts of them will reduce the time and energy needed and, of course, the possibility of human error. Utilizing the Unity game engine and the mixed reality toolkit, a set of components for rapid mixed reality development, we have managed to create a prototype application that takes advantage of the intuitive interactions and the visual elements that augmented reality offers to simplify mission tasks and make navigation and documentation much more flexible.
Hello, I'm Dimitris. I'm studying electrical engineering and I'm responsible for the software development of the AR application. Regarding the main menu, we wanted something intuitive that would serve as an easy gateway to the rest of the application. To that goal, we used a simple circular menu which appears with two consecutive air taps and goes away by tapping anywhere in the void. Earlier iterations of this menu included a drag-and-drop version that was scrapped pretty quickly. During the whole process, we wanted to showcase the usefulness of easily accessible digital information. A good example of that is the mission log, in which the astronaut may find written and visual instructions on their objectives. Two of the most important parts of the application are the map and the navigation mode. By opening the map, the astronaut is able to pinpoint the current location and examine potential paths to various points of interest. They are also able to select a new destination and view custom instructions to reach. Every path is also available in 3D view as an easily observable map. The logic behind the navigation is pretty simple. We divided the area in squares following a grid, and then we categorized each square either as occupied or non-occupied. Then, we applied the A-star algorithm on our grid in real time to get the final path updated every second. Following a similar thought process, we created a visual repair sequence which aims to aid the astronaut in case they need to repair some complex equipment. There is much more work needed to be done here, but a single sequence and model are showcased in the application. At the beginning, the idea behind the hologram placement was the desire to give the astronaut the ability to create custom paths by placing specific holograms, which would include geolocation data and other information. Although the original idea was scrapped due to complexity issues, we kept the placement and added the capability to take and save photographs in order to create the side screening and sampling holograms. The sampling hologram offers the astronaut a quick way to log the characteristics of the materials gathered during an EVA mission without the need of a physical log. The side-screening hologram, similarly, allows the astronaut to log text, notes, and a photo of a specific location. The great advantage of this method versus traditional pen and paper is the absence of physical materials, which keeps the astronaut's hands unoccupied, as well as the added benefit of leaving a holographic object with the gathered information at the side, which can easily be accessed by the future astronaut.
For simplicity's sake, metrics related to the vitals of the astronaut are easily accessible at all times, as well as a measure of the metabolic cost of their current path. The environmental conditions of the nearby area are tracked from the Weatherbox in real time. These data include radiation, temperature, and humidity measurements, offering the astronaut a better survival rate in the extreme conditions present.
Hey, I'm Chris. I'm responsible for the networking part of this project. As far as data flow is concerned, the data gathered from the sensors and the camera, which are attached to the Weatherbox, is transmitted through Ethernet connection to the control room. The sensor data is stored in a local database, and the video streaming coming from the camera is transmitted to the AR headset via Wi-Fi connection. For better data management, the network is broken down into two distinct parts. The first part consists of the path between the AR headset and the control room. This is the most data-heavy part, with the video streaming feature being responsible for almost all the data traffic, about 98%. The next part corresponds to traffic generated between the Weatherbox and the control room. This is the most important section where efficient data management is crucial in order not to surpass the threshold of 300 kilobits per second as given by Space Innovation instructions. According to our calculations, we can achieve this by lowering the quality of the camera frames.
The design logic of the Weatherbox was for it to function properly on Earth while also taking into account as many lunar restrictions as possible. One of those restrictions was the lack of atmosphere, making the temperature distribution on each side of the box uneven. Therefore, we decided to place a temperature sensor on each side for a better representation of this condition. In order to deal with the extreme temperatures on the Moon, we insulated the upper sides of the station with carbon fiber, while letting the bottom side function as a radiating plane, a form of passive cooling system. The body of the box was constructed out of 3mm aluminium in order to block alpha, beta, and cosmic radiation. On the other hand, gamma radiation will pass through and get measured by a sensor. Luckily, gamma rays do not disturb the function of the electronic circuits. Lastly, we mounted two wide-angle cameras on the sides, letting the user have a 360 view of its surroundings.
So, this was a very difficult mission, and we wanted to add some things to the future of our project. When it comes to the navigation, we wanted to add better spatial resolution, new maps, and a more intuitive approach to navigating the surface using other graphical elements rather than just lines. Wanted to actually measure the biometrics of the astronaut. And next slide, please. I can see. Tools for taking terrain images of other types, such as slope, multispectral, visible, or thermal, and porting them into the map feature, adding region indicators that are used in training regimes of astronauts already, such as time inside the region and order of the visitation, and the ability to change map indications. Thank you very much for your attention.
Thank you very much for your interesting explanation of your project. And I see we already have some questions in the chat. Somebody is asking, is it possible for the AR helmet to confuse an order with a random movement made by an astronaut's hand?
I think I can answer that. The prototype was meant to work with the Microsoft Hololens, and the first edition of the helmet only we can only use the click gesture. But in other iterations, there will be more gestures that are more specific, and there's also a clicker which can be thrown into the suit of the astronaut to more restrict.
I have another question, kind of related to the first one. Would gloves affect working with the AR helmet?
At this moment, yeah, they would definitely affect it, but in other iterations, if the clicking activity is part of the glove, it would not be a problem.
Thank you very much. Also, maybe from my side, the question, because I know that you also had the team from last year working on a similar project. Could you maybe remind a little bit or elaborate on the difference between this year project and last year project, maybe lessons learned or something, decisions that you had to make differently this year for the project?
When Spiros, the project manager of the last year's team, recruited us, he told us to try to generalize the project a bit, and that's the direction that we went to. We wanted to add some features, first of all, to make navigation much more flexible, because last year's project had static paths, and in this year, you can actually choose your location dynamically. And also tools for documented where are you going and what activity are you doing, how much time it takes. As for the lessons learned, I think this year's undertaking was much more difficult. We were 6 more members, and I think with the guidance of Spiros, we were just fine.
Great, thank you. Well, it's good to see that the project is continuing, and I just saw that somebody else was asking, are you going to continue to work on your prototype?
we were thinking of breaking the project up into maybe the more specific parts, maybe adding some parts with databases concerning the documentation, or making the navigation much more realistic because it's reduced to a pretty small area at the moment. Maybe in the future, more teams could take parts of the project and make them better.
Thank you very much. Now another type of question. So the equipment, would it be influenced by the radiation in the lunar environment?
As one of our reviewers has said, and the helmet that we're using, the Microsoft Hololens, has been tested in zero-G conditions and in the radiation-laden environment of the moon. And the hardware is still very limited. But we're hoping that in other editions, it could be protected by being incorporated into the real equipment of the astronaut.
Thank you very much. At the moment, I do not see any further questions, but this is also your chance. Maybe if you would like to say a few more words about your project this year, what was the biggest challenge or anything else that you would like to comment about your project?
Personally, can you hear me?
Yes.
Personally, I believe that the biggest challenge this year was the COVID pandemic and the communication, because we actually met in person not so many times, and pulling off the project, especially in the latest parts, was quite hard. And yeah. I also want to add that the direction we would like the project to go in the following years, if of course we find the right people, would be to integrate some control of maybe external robots or drones. I think that would be pretty interesting, but we're not there yet.
I see. Somebody is also asking, would you consider monitoring the physiological state of the astronaut?
The interface is there, but we didn't do that due to privacy reasons, and maybe in the future, I don't know.
Good, thank you very much. I do not see any further questions, so with that, I would like to thank you once again for the presentation, and thank you to all our viewers for the interesting. Oh, actually, I have one more question now. On behalf of Spiros Megalou, great job, Team LIGHT2. So congratulations again. It's unfortunate that we were not able to welcome you here in Switzerland. But thank you for presenting your project. And for everybody else, don't forget to join our other student project shows later this week. Thank you and goodbye.
Goodbye.